Okay, great. I think, Andrea, you can start. You can share your screen and we can start.
Okay. I think you should be able to see my screen now.
Yes.
Good. Okay, so welcome to the second part of the masterclass on the SASA module of Plumed. The idea today is to address the exercise that were given at the end of the last masterclass. So the idea behind the masterclass was to show how to use Plumed to use the SASA model for application implicit solvent simulations. So last time I gave you some idea what is SASA and how it is computed within the SASA module of Plumed. I explained you that there are two main algorithms for computing the SASA in Plumed. One is called SASA ASIL and the other is called SASA LCPO. I provided a brief summary of the theory behind the use of the SASA model in implicit solvent simulations. So the basic idea is to add to the total free energy of the protein a transfer term that describes the effect of temperature, pressure, and concentration of a given osmolyte, so that with this term, it is possible to describe implicitly a protein in a solvent that can be water, but can be also water in presence of an osmolyte at any temperature and pressure. And I described how this free energy of transfer term includes transfer free energy contributions, and I showed you how to compute them, and also a term called alpha, which is a fractional solvent accessibility. And this fractional solvent accessibility is what the SASA model compute through the LCPO algorithm or the algorithm by ASIL et al. Then the idea was to run simple exercises with the SASA model, and the model system was this short peptide here. It's a 15 residue peptide with this sequence here. And the idea was to start the simulations from an unfolded conformation of the model peptide and to run simulations at different conditions, including 298 Kelvin, 1 bar, and 0 molar concentration of an osmolyte, so pure water, 228 Kelvin, 1 bar, and 0 molar concentration, 348 Kelvin, 298 Kelvin, 1 bar, and 10 molar concentration of urea, and then 298 Kelvin and 3 kilobar. And the basic idea was to run each simulation for 5 nanoseconds. We can then therefore start the simulations, starting from exercise 1. I introduced already exercise 1 at the end of the last lecture, but it does no harm to restart from here now. So the first thing you will need to do is to install the software you need for the exercises. So first the Plumed environment, and you can find instructions here, and then the Amber environment, and then you need to stack the two environments together. I did that already. So here I have activated the Plumed environment, and then the Amber environment, and I have stacked the two environments together and updated the Plumed kernel so that Plumed and Amber can communicate during the exercises. Then what you will need to do is to download the folder with the input files for the exercises. So we can do that. I did it already actually, but I can create a new folder. And we can restart together. So you need to run this command to download the folder with the exercises. And the folder is just a very small folder that contains README file, pretty much useless. And then in the SASA module folder, you have 5 different subfolders, one per each exercise. So exercise number 1 is the first simulation at 298 Kelvin. You have different files here. This first file, AAQAA.prmtop is just a topology file for the AAQAA model molecule. So it contains all the information about the bonded parameters of the peptide. This file here is an input file for Amber that contains details about the simulation. So we want to run an implicit solvent simulation with a generalized Born approximation for electrostatics and a solvent accessible surface area approximation for the nonpolar contribution. And then we are setting also the dielectric of the solvent. Here we specify how often we want to save information, the restart file information, the energy information, and the coordinates. We use Langevin dynamics at the temperature of 298 Kelvin for this number of steps at a 2 femtoseconds time step. We use an infinite cutoff because we don't want to have a finite cutoff in implicit solvent simulations. And we also tell Amber that we want to use Plumed. And specifically, we want Amber to read a Plumed file called plumed.dat. This NCRST file is the starting configuration of the system. Then we also have a starting confirmation of the protein. You can have a look at this. So it's an unfolded conformation. Without any secondary structure content. And then the other files are just files that we will use later on for the analysis, these 3 files here, and we have the plume.dat file, obviously. So what we are providing as input is again this PDV file of the protein in the unfolded conformation, and then we are monitoring the radius of gyration of the whole protein, the antiparallel and parallel beta sheet content, and also the alpha helical content of AAQAA, and this protein should fold into a alpha helix. And then we are printing all of this information to a file called Culver. We are not even using the SASA module here because the simulation is at 298 Kelvin, and in absence of any pressure effects or any osmolalite effects, so we don't need to include a transfer-free energy contribution here. Running the simulation is pretty straightforward. You had already the command here. So what we are using is the Sander model of Amber. I will copy this to make things quicker. And so if you run this command, we are providing to the command the input file with all the info about the simulation in Amber. And the Sander, while running the simulation, will output an output file .out with the information of the current time step and so on. We are providing the initial confirmation, the NCRST file the topology, the PRM top file, and we are generating an NCRST file with the last frame and also a trajectory file with extension NC. So the simulation should take, I think, about 1 or 2 hours on a normal laptop, so you didn't even require to use a, let's say, a cluster for this masterclass. Obviously, I won't let the simulation run completely, but I'll just have a quick look at the output files. So these out files, again, contain information about the single frames run by the simulation. And then the callbar file obviously is continuously updated and contains information about time, radius of gyration, and secondary structure content as we specified in the Plumed input file. And Amber also generates an MD info file where we have the information about the last time step that has been run, and also the estimated time remaining for the simulation, so about 1.2 hours on my laptop. I will stop the simulation here. I ran it already, so we can have, in any case, a look at the results. So this is the simulation completely run. The first simulation, we can have a look at the evolution of the radius of gyration of the protein during the simulation time over the 5 nanoseconds. So this is the evolution of the radius of gyration. As you can see, it starts from an extended conformation with a radius of gyration of about 1.5 nanometers, and then the radius of gyration quickly goes down, and then slightly increases a little bit over the simulation time. What we can deduce from here is that the protein goes to a more collapsed conformation, and then this slight expansion here is due to the formation of the secondary structure, as we will see soon. The protein is A is supposed to be alpha helix. Alpha helix is shown in the callbar file as the 1, 2, 3, 4, 5th column. So I will plot here the 5th column, and we can see indeed that the simulation starts from a very unfolded protein at the beginning with no alpha helix, and then the alpha helix content goes up, and the protein is finally in a completely folded state in the last nanosecond of the simulation. What you should also notice that the folding process is very fast. It is fast in general for AAQAA, but the speed of the folding process is accelerated by the implicit solvent conditions. Folding would be much slower in explicit solvent simulation.
Can I make a question now?
Yeah, sure.
Because it looks like what is going on with this is like a kind of prediction of the tertiary structure of the system, right?
Yeah, true. I mean, the system is so simple in this case. It's just a 15 residue protein that in this case this is possible. Yes, exactly.
Yeah, and actually, what is the bias for the force that is being used here to drive the simulation? It's just the fact of the simulation of an implicit solvent through the SASA, or is there any other bias force that we are applying here? No, it's only the implicit solvent simulation.
Exactly. That's the only bias here. We're not running, for instance, a metadynamic simulation here. It's just the implicit solvent force field that we are applying. Yeah.
And, 2 more questions. One is that if this can be also transported to GROMACS.
Yes, I mean, obviously Plumed can be incorporated into GROMACS, and I have run some implicit solvent calculations in GROMACS before. The main issue is that GROMACS is not really supporting much implicit solvent runs, so there is not much support in latest versions of GROMACS especially. And also, while in Amber it is possible to parallelize implicit solvent calculations, in GROMACS this is not feasible. The developers of GROMACS decided not to, let's say, invest much attention in implicit solvent calculations, and so they decided not to parallelize this part of their script. And if you want to run an implicit solvent calculation in GROMACS, you have to do a serial calculation, which is quite slow then, for sure. That's the main problem.
And last question is, what happens if we try to implement this into a bigger peptide? I don't know, 3 or 4 times bigger than this.
Yeah, I did this type of calculations in the past. Obviously, predicting the secondary and tertiary structure there is much harder. It's still complicated. It's still, let's say, at the moment out of reach for larger peptides. For sure, you can see the protein being collapsed and forming some secondary structure or tertiary structure in a time frame that is shorter compared to the explicit solvent counterpart, but saying that you can really fold, let's say, a large protein, no, this is still not feasible. If you want to start from a fold conformation and see unfolding, this is very quick in implicit solvent calculations, much quicker than in explicit solvent, but folding is still problematic.
Thank you.
Okay, thanks for the questions. Very nice questions. Okay, so what we can also have a look here, we could have a look at the trajectory on VMD, maybe how it proceeds. Just make it a little bit nicer so that you can see more. To molecule, I will load into the PDB file the trajectory. Okay. VMD is a sort of bias actually in the, yeah, it should work out. Yeah, VMD is sort of bias in the attribution of the secondary structure when you run a Wool trajectory, and it is how it is. But what you can see is that the protein over the simulation time tends to assume a more collapsed state, and then starting from an unfolded structure, it progressively folds the alpha helix. And the process is actually very fast because in implicit solvent, you don't have any retardation effects due to viscosity. So this is the first simulation at 298 Kelvin. And here we did not even apply actually the SASA model. So this was only a preliminary exercise. What I would like to focus on more now is exercises 2 to 5, where we have to apply the SASA model. So here is the list of the exercises. So exercise 2 is at 228 Kelvin. In the folder I uploaded on GitHub, there was no plumed file, or let's say the plumed file was completely empty. So the idea was that you should write the plumed file yourself using as template the plumed file provided in exercise 1. So the first thing we could do is looking at how the plumed file for exercise 2 looks like. So here is the plumed file. It is quite similar to the plumed file employed during exercise 1. We again provide a protein structure in input using the molinfo keyword, and I monitor exactly the same variables. So the radius of gyration the anti-parallel beta sheet content, the parallel beta sheet content, the alpha helix content of the protein. But then I am introducing another variable here. So this is the SASA model. I'm using the SASA-Hazel function. So the faster algorithm by Hazel et al. As I mentioned, the LCPO algorithm is a little bit more accurate, but the algorithm by Hazel is faster. And that's why I suggested you to use this algorithm for the exercises of this masterclass. I am applying the SASA-Hazel function to the whole protein, so atoms 1 to 174, and I'm using the transfer type. If you remember, there are two types for the SASA model. One type is total, and there you compute the full SASA, and then you can use the SASA as a collective variable in metadynamics or for monitoring the SASA during the simulation. While the transfer type used here is what we need to use the SASA function to compute the transfer-free energy term. The neighbor list stride keyword is used to specify the frequency with which we want to update the neighbor list during the calculation, and here is set to 10. It is the default, and based on my experience, it works pretty well, so I wouldn't recommend you to change it too much. What we need to specify here is either a delta G file, including the specific transfer-free energy contributions of the different side chains and of the different backbone groups for the peptide, or we need to specify the approach we want to use for the computation of the transfer-free energy contributions due to temperature. As I explained during the last lecture, for the computation of transfer-free energy contributions describing the effect of temperature, we can use two different approaches. The two different approaches refer to the mathematical derivation used for the extraction of the free energy of transfer values. These two approaches are called approach 2 or approach 3, and here I'm selecting approach 2. So the software itself, PLUMED itself, will compute the transfer-free energy contributions based on approach 2. What I'm then doing, I am using the bias value keyword to introduce this transfer-free energy term into the system potential. So in this way, the system is biased through this transfer-free energy term. And then I am again printing all this information to the Culver file, so transversal gyration, secondary structural content, and also now the transfer-free energy term and the over bias that should actually be identical. So the command for running the simulation through Sander is the same that we used previously, and the output files are exactly the same. So unless you have questions in this regard, I won't go much into details on this aspect, but what I want to show is the output of the simulation. It should again take, let's say, between 1 and 3 hours on normal laptop to run. So I want to show you the Culver file this time. So it's a bit bigger. It contains, apart from the normal variables we already observed in the previous exercise, also the transfer-free energy term, this term here in kilojoules per mole, that is then added as a bias to the simulation itself. We can do a plot again of significant, let's say, variables during the simulation time. So I plot again the radius of gyration, and maybe as a reference, I plot also the radius of gyration of the previous exercise. So the simulation in black is the simulation number 2 at 228 Kelvin, while the curve in red here is the third simulation at 298. So in terms of radius of gyration, we don't see much of a difference. In both cases, the radius of gyration decreases over the simulation time, and the protein eventually goes to a more collapsed state. Let's have a look now at the alpha helical content. The alpha helical content is actually quite different in this case. While at 298 Kelvin, the protein folds to a helix, at 228 Kelvin, the protein mostly remains in a state with quite reduced secondary structure content. And this, of course, because we are already below the cold denaturation temperature of the protein. So in this case, complete refolding is not possible. I will plot also the evolution of the transfer-free energy term over time for this simulation. So this is actually the evolution of the transfer-free energy term. What we can understand from here is that there are two opposing contributions during the simulation time. The first one is the, let's say, the contribution of the force field itself that would like the protein to fold into alpha helix. And the second contribution is the transfer-free energy contribution that pushes the protein towards an unfolded conformation. This increase in the transfer-free energy term is due to the opposing force field contribution that pushes the protein towards a folded state. What we can also do is to use some files that are provided in the folder on GitHub. So this script rg alpha file, it is a script that performs an analysis on the distribution of the radius of gyration and alpha helical content of the system during the simulation. So to run this script, you just need to provide as input the Culver file, and then you can use then the file produces as output a file called normfel.dat that is basically a free energy surface, and we can visualize this file using nuplot. There is also in the GitHub folder online a nuplot file that you can use to plot the normfel.dat file. So I will load this nuplot file, and this is the output. So at 228 Kelvin, we have the following distribution of radius of gyration and alpha helical content. The protein can sample states with quite high alpha helical content, but the most sample conformation displayed here in this bluish color are conformations with a quite large radius of gyration and a quite reduced alpha helical content. Exercise number 3 is quite similar. It just performs the calculations at a different temperature of 348 Kelvin. So in this case, the plumed file will actually be quite similar. So the let's say the initial part of the Plume file is identical to the previous one. So again, providing as input the PDB file of the protein and monitoring radius of gyration and secondary structure content. And then the way we call the SASA function is actually identical. We again use the SASA ACE algorithm, and nothing basically changes. We don't even need to specify the temperature here because Plume directly reads the temperature of the simulation from the AMD code. So no need to change anything here. We can again have a look also in this case at the radius of gyration and alpha helix content. We have again in black the simulation at 348 Kelvin. In black the simulation at 348 Kelvin, and in red the simulation at 298 Kelvin. Also in this case, the radius of gyration decreases over time and reaches a similar value at both 298 Kelvin and 348 Kelvin. Interesting is the evolution of the alpha helical content. Again, in this case, while at 298 Kelvin shows, in this case, the free energy surface is much more expanded. So the number of states that can be sampled is much larger, and we expect this because we are working at a higher temperature, so in conditions of much larger entropy. And the system, the model protein AAQAA can sample states with a huge variety of values of radius of gyration and alpha helix. Let's move now to exercises 4 and 5 that are actually a bit different, because now we want to include the effect of an osmolate and of pressure. So in this, the Plume file needs to be different. We cannot anymore use the approach keyword because we don't aim to describe the effect of temperature here. So let's first have a look at the PLUMED file. We are again monitoring the same variables as before. What we should focus on is the way we call the algorithm. We again compute the free energy of transfer term for all of the residues within the protein. So for atoms 1 to 174, the type is always transfer, and we don't change the stride for the neighbor list update. But what changes is this last keyword here. Now we use the keyword delta G file to provide Plumed with a delta G.dat file as input. This delta G.dat file includes the transfer free energy contributions that Plume needs to know to compute the transfer free energy term. Specifically, exercise 4 aimed at simulating a AQAA at 298 Kelvin, so let's say ambient temperature, and in presence of 10 molar urea concentration. So this delta G.dat file needs to include the free energy of transfer contributions corresponding to urea. how do we generate this delta G.dat file? As I explained during the first lecture, I have written and uploaded on GitHub a Python script called delta G calculation.pl that you can freely download, and that computes the free energy of transfer contributions for you. So on GitHub, you can also find a README for this Python script that explains you how to use the script. So here is, for instance, the explanation of the usage. You need to call the script and then provide as input variables for the script the type of osmolate you want to simulate, the osmolate concentration, the value of the temperature you want to describe, the type of approach you want to use to describe the effect of temperature. So this can be either approach 2 or approach 3, as I was discussing before, and also the pressure value. So let's try to apply this script here. I have it in my folder. It's here. So Python 3 delta G calculation.py. So we want to simulate in these exercise for urea, and urea appears within the osmolate types we can simulate. The osmolate type can be sucrose, urea, TMAO, proline, betaine, or none, in case you don't want any osmolate. So in our case, we want to simulate urea. Then we need to specify the osmolate concentration. The concentration needs to be provided in moles per liter. So we want a 10 molar concentration of urea, so we need to add 10 here. Then we need to specify the temperature value. Our aim is to work at 298 Kelvin. At 298 Kelvin, actually the contribution of temperature to the transfer-free energy term is 0, no matter which approach we decide to use. So if you insert 298 value here, there will be no contribution of temperature to the final delta G.dat file, to the file including the transfer-free energy contribution. So we can then select either approach 2 or 3. There is no difference at all. And then we need to specify the pressure value in bar, and we want to work at 1 bar in our simulation. So I run the script, and the script outputs a file called delta G.dat. We can have a look at this file. This file includes in the first column all the different side chains, so from alanine to valine, and also the backbone group, and lists in the second column the values of the transfer-free energy contributions. A negative value of the transfer-free energy contribution means that we are moving the side chain or the backbone to a better solvent. As we all know, urea is a good solvent for the peptide backbone, and this is why this transfer-free energy contribution for the backbone is quite negative. And this is actually also what drives unfolding. We can then again run the simulation using the same Sander command, and the Colvar file will again include the different terms we described before, so time, radiative gyration, secondary structure content, and the transfer-free energy value as function of time. In the case of urea, the denaturation of the AA protein is less pronounced, but you can still have a look, for instance, of the evolution of the alpha helical content over time compared to the simulation at 298 Kelvin in pure water. And this is what happens. While at 298 Kelvin, we have a completely folded protein at the end of the trajectory. In presence of 10 molar urea, actually the alpha helix content is very reduced. We basically have a protein that remains in the turn or coil conformation. Urea is inhibiting the secondary structure formation in A2AA, and that's what we would expect. Urea is a protein denaturant commonly used in denaturing experiments. We can again have a look at the distribution of the radius of gyration and alpha helix. And here is how the final distribution looks like. So actually we have a very compact conformation, and it should probably change the range here for the x-axis, but let's say the structure is very compact, so we can also have a look at the radius of gyration afterwards, and the alpha helix content, as we discussed, is very low. So let's have a look also at the radius of gyration over the simulation time, and let's compare it to the simulation in pure water. So the simulation in pure water, the red curve, the simulation in black is the simulation, the curve in black corresponds to the simulation in 10 molar urea. What happened is in both cases, we got towards a collapsed state, but then in water, the red curve, the collapsed state slightly expands to form a secondary structure, a alpha helix. Well, this is not possible in presence of 10 molar urea. And the protein remains in a collapsed conformation, but without any secondary structure. Finally, let's move to exercise number 5. So in exercise number 5, the idea was to discuss the effect of pressure. So specifically of a quite high value of pressure of around 3 kilobars. These values of pressure are, let's say, those that are generally necessary to unfold a protein. Generally below 2 kilobars, not much happens to a protein structure, and that's why for these masterclass exercises I decided to work at a quite high value of pressure of 3 kilobar. Also, the effect of pressure is generally more pronounced for globular proteins that have quite some voids in the native state, because these are the points that drive pressure unfolding. In our case, with this small floating residue protein, we don't have many voids within the native state, and so the effect of pressure is not so marked, I would say. But let's have a look at the plumed file first. So this plumed file now looks very similar to the previous one used to describe the effect of urea. We again call the Sasa-Hazel function with the transfer type, and we again use the delta G file keyword to provide as input a delta G .dat file. And then, as usual, we use the bias value function to include the transfer free energy term in the system potential. The delta G.dat file, we can again produce it using the delta G calculation.py script that I described before. So let's again run the delta G calculation script. So I'm very lazy, so I recall the previous comment I used. So in this case, we don't want to describe any osmolite. So here we will use none, osmolite type. Then we also don't want any concentration. So I insert here 0 as moles per liter. The temperature is again 298 Kelvin. And as I specified before, when we work at 298 Kelvin, approaches 2 and 3 are identical in the sense they don't give any contribution. And the last value here, as specified in the README file provided together with the delta G calculation script, is the value of the pressure in bars. So we need to insert here 3000. And then we can again run. Maybe I can also show you that it does something. So we can run the script and it produces the G.dat file that has the same aspect as before. So again, it is in the first column, the different sidechains and backbone, and in the second column, the transfer free energy contributions. They are all negative in this case, because we are going to a higher pressure, so to a better solvent for the protein, and this is actually what then drives the unfolding process. We can again have a look. So with this plumed file, the simulation run again as usual with the Sander module of Amber. And let's have a look at the results. So at the evolution, for instance, of the radius of gyration, the radius of gyration remains quite compact at both 3 kilobars, the curve in black, and 1 bar, the curve in red. And the radius of gyration, the alpha helical content, instead has the following evolution. So again, the red curve is the reference simulation collected during exercise 1 at 298 Kelvin and 1 bar, and the black curve is the simulation at 298 Kelvin and 3 kilobars. Also in this case, you can see that at 3 kilobars, we have much more pronounced oscillations, and that is because the gain pressure is promoting instability of the protein. As I mentioned, in this case, the effect of pressure is not so marked because the AAQAA molecule has no voids within the native fold. If we again use the script RG alpha bash file provided in the GitHub folder to analyze the distribution of alpha helix and radius of gyration, I won't do that here again because it's, let's say, the same approach as before. We obtain a graph like this one that we can compare, for instance, with the graph of the reference simulation at 298 Kelvin. So while at 298 Kelvin and 1 kilobar, we are restricted in this area of the free energy surface, so small Rg and high alpha helical content. At 298 Kelvin and 3 kilobars, we explore a larger conformational space, and also conformations with reduced alpha helix content and larger radius of gyration are now feasible. So last, I would like to provide you a summary of all of the simulations. What I did, I plotted the evolution of the alpha helical content as function of simulation time for all of the simulation or for all of the exercises we performed so far. The red curve here is the one corresponding to exercise one, so 298 Kelvin, and we see refolding of the protein, very fast refolding. All the remaining conditions for during exercises 2 to 5 result in at least partial unfolding with reduced secondary structure of the protein, and that's exactly what we would expect because high and low temperatures result in hot and cold unfolding respectively. Urea, we know it is a potent denaturant, and also pressure. We know that at these high values of pressure, it is likely to have pressure-induced unfolding of a protein. The effect of all of these, let's say, variables, so temperature, osmolalite, and pressure has been included in the molecular dynamics simulations through a transfer-free energy term that has been linked to the system potential through the SASA module of PLUMED. And actually, we are happy because at least it seems that this transfer-free energy term does exactly what it is expected to do. And also what you should think of is that the advantage of these implicit solvent simulations is that while observing refolding and also observing these differences in explicit solvent runs would require much longer trajectories, here we can see clearly a difference in the behavior of the peptide in only 5 nanoseconds, and with a quite reduced computational cost, because the whole of these 5 simulations would require less than, let's say, 10 hours on my home laptop, for instance. So they don't require lots of computational power. So this is basically what I wanted you to show during this second lecture. And now, actually, if you have any questions or doubts about these calculations, also I would like to ask also the Plume developers if it is fine for them if I also include some of these results then on the Plume website in the tutorial for this masterclass, so that they are also available and interested people can have a look also the results and compare their solution to mine. What do you think? Is this feasible, or is this something that should be avoided?
Yeah, of course you can. So I think in the past master classes we added something like in the same GitHub repository a directory with solutions, something like that.
Okay, yeah, I can add the solutions there.
Thinking about it, maybe I did it in a hidden directory with a dot name, but just to avoid people finding it really immediately.
Or maybe I can add a comment at the end of the masterclass, let's say, page on Plume to say that there is also a separate folder with the solutions, but students shouldn't look at that.
Yeah, it's fine. It's fine. I think it's better to add it if you have it. Yeah.
Okay, perfect. Thanks.
Just to ask if this module is available by default during compilation, or we have to use a specific flags to compile it?
Yeah, this model is an additional model, and you have to add a line during configuration. So I will open it's here actually. So if you let's say install Plumed by yourself, so you don't use the Conda version of the masterclass, you have to add these line here, enable model SASA to your configure command when building Plumed, if you then want to be able to use it. Yes.
Thank you.
You're welcome. I see there are actually other. Maybe I will stop sharing. Are there other questions or doubts or concerns about these exercises? Something else that you would like me to clarify? I could count out to 10, so I think it's
yeah. So yeah, if there are no questions, yeah. So then let's thank again Andrea, and
see you.
And that's it. Okay. Bye bye to everyone.
Thank you very much. Bye bye.
Bye.